Hi everyone, welcome to the section on loss functions. So the loss functions are also known as error functions, cost function, and objective functions. So in any model, whether it belongs to a classical machine learning or a deep learning, our purpose is to calculate the loss function and then to reduce the loss function. When we reduce the loss function, it means we are going to improve the performance of our model. And we reduce the loss function by updating the weights and bias of the model. Let's see what we are going to cover in this section. So we have only three topics which we have to cover in this section. The first loss function is a mean square loss function or MSC loss function. This loss function is usually used when we have to do regression with the help of machine learning model. So it is very useful when we have to perform regression. So we will learn this mean square error loss function in this section with the help of a small numerical example. The second important function is cross entropy loss function. This is probability based loss function, and it is used with the neural networks when we have to perform classification, whether it is a binary classification or a multi-class classification. So we use cross entropy loss function when we have to perform classification. The third is a softmax function. So basically, softmax function is an activation function. It is used with the cross entropy loss. And the purpose is that softmax function transform the cross entropy loss values into the form which added to 1. That is, it transform the probabilities into the true representation. What happens is usually the values which comes out after cross entropy loss are the values. If we add them, we cannot get 1. So then we use softmax function. So softmax function normalize those values and transform them into the values whose sum is equals to 1. So these are the topics which we are going to cover in this section. Thanks for listening, and I will see you in the section. Hi everyone, welcome to this lecture. So in this lecture, we will learn about mean square error or MSC loss function, which is one of the most commonly used loss function in neural networks. So how to calculate mean square error or MSC loss function? So if you see this equation is for MSC loss function. If we see here, y minus y pred, this is our error. So if we square the error, it will become a square error. And then if we take the mean of the square error, that is by summing the error for each sample and then divide by the total number of sample, it will become mean square error. So if we see the name mean square error, where error comes last, but we calculate the error first. So the word error come last in MSC, but we calculate the error first. So first we calculate the error by subtracting y minus y pred, that is subtracting the predicted labels by a model from the original or actual labels. So that will give us the error. Then we square, and then finally we take the mean, so that this become mean square error. Here is a small example which explain how to calculate the mean square error. So we have three samples, 1, 2, and 3. For first sample, the value of actual label, that is y, is 60. The value of predicted label is 71. So here the error is -1. Okay, so if I square -11, so if I square -11, I will get 121. Similarly, here y is 50 for the second sample, y pred is 52. So if I want to calculate the error for this sample, I will get -2, and square of -2 is 4. Similarly, for the last or the third sample, we have error equals to 5. If I square the error, I will get 25. So all these are squared error. If I sum them and divide by 3, like here, it will get mean square error. Since we have 3 samples in this dataset, therefore, if I add the squared error and divide by 3, I will get mean square error. So this is the method of finding the mean square error, and the loss function will becomes the mean square error loss function. So MSC loss function is used in regression analysis, where we have to predict the continuous value. Like if we have to predict the price of a house, the salary of a person, or the price of some car, in that case, we have to perform regression. So in regression, we use MSC loss function. The other advantage of MSE loss function is that the loss surface is convex and we can easily apply convex optimization. So this is our MSE loss function. So it is a square loss function. Therefore, the surface is like this in the form of convex. So in convex shape, the advantage is that we have one global minimum point where we can reach easily. So if at the start of the process we are here, so we can move toward this zero value where the slope of the surface is zero in small steps. So we can take a small step and we can easily reach to the global minimum of this surface. So this is the advantage of MSE loss function, that the loss surface is in the shape of convex and we can easily apply convex optimization in order to get the zero value of the loss function. So we can easily reduce the MSE loss function due to its nature, due to its convex nature. So in this lecture, we learn about MSE loss function, which is one of the commonly used loss function in neural network. It is mostly used in regression analysis and it is easy to reduce because it has convex shape. So I hope you understood this lecture. Thanks for listening and I will see you in the next lecture. Hi everyone, welcome to this lecture. So in this lecture, we are going to learn about another loss function, which is cross entropy loss function. It is also one of the most commonly used loss function in neural networks, and it is used when we have to perform classification with the help of the loss function. So previously we learned about MSE loss function, which is mostly used in regression applications. So cross entropy loss is mostly used when we have to perform classification with the help of neural network. So before going into cross entropy loss, we have to understand the concept of a negative log function. If we see here, this is the plot of a negative log function, where on x-axis, I have a value of x, and on y-axis, I have a negative log of x. So if we see here, we can see that if we increase the value of x, the value of negative log x decreases. So this is very important property which we will use in order to understand the concept of cross entropy loss. So we can see here, if x is equals to 0.03, that is very small value of x. So we are somewhere here. If x is equals to 0.03, we are very close to 0. In that case, the negative of log x is 3.5. So if x is very, very small, we can see that the value is large, that is 3.5. Similarly, if we increase the value of x and now we are at 0.9. So here x is equals to 1 and 0.9 means we are somewhere here. In that case, the value of negative log x is very small and it is approximately equals to 0.1. So we can see that if we increase the value of x, the value of negative log x decreases. So this negative log x is high for the small value of x and it is low for the large value of x. Now this is the equation for the cross entropy loss. So here we have few important parameters or variable in this equation. So first variable is y. Y is actual class label or it is ground truth. P is the predicted probability for the class. That is, it is the probability of the class which is predicted by the model. Okay. N is number of samples. Here N is number of sample and C is number of classes. So this is cross entropy loss. So it is based on the logarithmic value for the probability of the class predicted by the model. So this is called binary cross entropy loss. So cross entropy loss becomes binary cross entropy loss if we set number of classes is equals to 2. So for 2 classes, this is the form of BCE or binary cross entropy loss. So here we can see that we have 2 terms. This is first term and after the sign of addition, this is second term. Here we have y and here we have 1 minus y. Here we have probability P and here we have probability of 1 minus P. Now for simplicity and for better understanding, suppose n is equals to 1, that is we have only one sample. So if we have only one sample, this is the form of binary cross entropy loss. Now again we can see that we have two terms. Here we have a negative sign, but we have a two terms. That is, this is our first term and this is our second term. Now the important thing is that we cannot use both terms simultaneously. That is, if y is equals to 1, we will use this term to calculate the loss, and if y is equals to 0, we will use this term after this plus sign in order to calculate the loss. Now how it is happening? So basically, if your label is 1, because we are doing the binary classification, in that case we have two labels, that is 0 and 1. So if your y is 1, if your label is 1, and if you put 1 in both of the terms where y is present, then this term will be 0. The second term will be 0, because if I put y is equals to 1 here, then 1 minus 1 is equals to 0. That is, this term will not be used to calculate the loss if y is equals to 1, and I will use only that term. That is, if I put y is equals to 1 here and y is equals to 1 here, this term becomes 0, and I will get only negative log of p. So that is the equation of binary cross entropy loss if my label is 1. If my label is 0, that is y is equals to 0, and I put y0 here and y0 here, then due to 0, this term becomes 0, because if I multiply log of p with 0, I will get 0. But if I put 0 here, then I will get 1, because 1 minus 0 is equals to 1. So that term will be used as calculation for the loss, that is for binary cross entropy loss. So we have observed that in our binary cross entropy loss equation, we have two terms. So the first term will be used when y is equals to 1, and the second term will be used to calculate the loss if y is equals to 0. So this is the form of the first term when y is equals to 1, and this is the form of the second term of this equation when y is equals to 0. Now, there are three cases. Now, case one is when loss is high and need to minimize. So the question is when the loss is high. So here are the two situations where the loss is high. If y is equals to 1 and the probability of prediction is 0.1, in that case, we will use this part of the equation in order to calculate the loss, that is minus log of pi. We have seen this in the previous slide. So if y is equals to 1, and p is equals to 0.1, in that case, our loss is negative log of 0.1. And we know that if inside the negative log, we have a small value, then the negative log is high. So if y is equals to 1 and p is a small value, in that case, loss is high. The other possibility is if you have a second label, that is y is equals to 0 and p is high, that is 0.9. In that case, we will use this part of the equation in order to calculate the loss. Okay, so if your p is 0.9 and you put p is equals to 0.9 here, you will get minus log 1 minus 0.9. This again will become log of 0.1, and this value again becomes high. So here are the two situations with y is equals to 1 and y is equals to 0 when loss is high and we need to minimize. So the loss is high because loss depend upon the negative of the log. So if there is a small value in the negative of a log, we will get a high loss. Now this is the situation when loss is low. So when loss is low and your label is 1, that is y is equals to 1, in that case probability is 0.9. And a negative log of 0.9 is a small value, because we have learned if a large value, because this is a large value as far as the probability is considered. So this value is large, and we know that if we pass a large value to negative of log, it is small. It will give us the small value. Similarly, if y is equals to 0, then we will use this part of the equation in order to calculate the loss. So here y is equals to 0 and p is equals to 0.1. So if you put p is equals to 0.1 here, then you will get 1 minus 0.1, which is also equals to 0.9, and we will get the low value of the loss. This is the ideal scenario. So if y is equals to 1 and p is also 1, then minus log of 1 is equals to 0. And similarly, in the second case, if y is equals to 0 and p is also 0, then negative log 1 minus 0 becomes negative log of 1, which is equals to 0. So these are the three possible cases which appears with the cross entropy loss, and cross entropy loss depends upon the negative value of the log. So in that case, since we have a concept that if we have a small value inside the negative log, it will give us a high value. So in this lecture, we learn about the cross entropy loss. In order to make our understanding easy, we convert the cross entropy loss into binary cross entropy loss. We saw that the binary cross entropy loss has two terms, and we cannot use both terms simultaneously in order to calculate the loss. If our level is 1, then we will use this term in order to calculate the loss, and if our level is 0, then we will use the second term of BCE in order to calculate the loss. So I hope you understood this lecture. You understood how cross entropy loss works, and it depends upon the negative log of the value. Thanks for listening, and I will see you in the next lecture. Hi everyone, welcome to this lecture. So in this lecture, we are going to learn about very important function which is called as softmax function. So these are the properties of a softmax function. So cross entropy loss uses softmax as an activation function. So basically softmax function is an activation function and it is used with cross entropy loss. The softmax turns all the class probabilities to values that sum up to 1. Now we know that the cross entropy loss depends upon the probabilities which are given by the model or which are predicted by the model. So what softmax does with that probability, that it transforms those probabilities to such values that can sum up to 1. It is used for multi-class classification. Multi-class classifications means if we have more than 2 classes in our data set, then it will be used with the cross entropy loss. For 2 categories, softmax equals to sigmoid. So if we have only 2 labels, if we have 2 categories in our data set, in that case, softmax is equal to the sigmoid function. So these are the 4 properties of a softmax function, that it is an activation function which is being used with cross entropy loss, and the advantage is it converts the class probabilities of a cross entropy loss into the form that we can add them to equals to 1. So here is the explanation that how softmax functions work. So this is the equation of a softmax function. We can see that here we have the exponent and here we have the sum of all the exponent. So this is our normalization term. We divide every exponent with the sum of the exponent. Let's understand the working of softmax function or this equation with the help of example. So suppose we have 3 values. This is a multi-class problem. We have 3 values. Each value is about a label. So this is a vector created with the help of cross entropy loss. So this is a vector which is created by the output layer of a neural network or a classification layer of a neural network. So we have 3 values. So basically we have 3 classes. If I add them, I will not get 1. So these are the values which are predicted by a cross entropy loss about 3 different classes. So what will happen? I will apply a softmax function in order to get the values where if I add them, I will get a 1. So the first step is to calculate the exponent of each value inside this Z vector. So the exponent of minus 1.28 is 0.278. The exponent of 0.53 is 1.7. And the exponent of 0.87 is 2.38. So these are the 3 values which are the exponent of these. Okay. Now, if I adding all the exponent values, I will get 4.36. That is, if I add 0.278, if I add 1.7 and 2.38, I will get 4.36. So this 4.36 represent the denominator of this equation. This is the sum of exponent. This is the individual exponent value, that is either 0.78, 1.7 or 2.38, and this is the sum of all the exponent value, that is this is the a normalization term, which is 4.36 in this particular example. Now normalize each component, that is divide the value with the normalized value. So first step is to divide 0.278 by 4.36. Then divide the second exponent with 4.36 here, and then divide 2.38 with the exponent or the sum of exponent or the normalized value. So we will get 0.06, 0.4, and 0.54. So if I add them, I will get a value equals to 1. So we can see that at the end of the output layer or at the end of the classification layer, I had these three values which are generated by cross entropy loss. The sum of these values were not equal to 1. In that case, I used softmax function. Softmax function transform these values into these three values, and if I sum these three values, I will get equals to 1. So this is the equation of a softmax function, and we have applied this equation on this vector. So this is the exponent of each term present in the vector, output vector, and this is the normalization term, which is the sum of all the exponent value. So in that way, we use this equation on this vector. We first find the exponent, then the sum of exponent, then we normalize each exponent. After normalization, we reach up to the values that if we add them, we will get the sum equals to 1. So in this way, we learn how softmax function is used with cross entropy loss in order to transform the cross entropy loss values into the values whose sum is equals to 1. Now, here is another explanation of the same example. We have this z vector. These are the exponent value of each z vector, and these are the normalization value. And if I add them, I will get equals to 1. So this is the result of a cross entropy loss for multi-class problem. And after applying softmax function, we will get these three values whose sum is equals to 1. So this is the advantage of softmax function, that it transforms the cross entropy loss value into the loss values, which are the true representations of the probability, that if I add them, I will get the value equals to 1. Now here is a proof that if we use softmax function for two classes, it will be equal to sigmoid function. So this is the equation of a softmax function. Now suppose we have two classes, x and y. Now for first value, here I am using ex, and this is the sum of exponent. So this is my individual value, and this is the sum of exponent. This is this equation, this value or the numerator of the equation, and this is the denominator of the equation. Okay, now the next step is subtract x from each of the exponent value. That is, subtract x from x for this term, subtract x from x for this term, and subtract x from y of this term. So it will become x minus x, it will become x minus x, and it will become y minus x. So x minus x will become 0. And here we also get 0, and here we get y minus x. So anything raised to power 0 is 1. So in the numerator, we will get 1. And in the first term of the denominator, we will also get 1. And here we have exponent raised to minus x minus y. If I take minus common here, if I take minus common, it will become x minus y. So if I replace x minus y with t, in that case, I can see that this is the equation of a sigmoid function, which we learned in the previous section of this course, that is section on activation function. So with this small mathematics, we have proved that softmax function for two classes will be equals to the sigmoid function. So in this lecture, we learn about the softmax function. We learn that it is a very important activation function, which is used with binary cross entropy loss. So we learned that softmax function transform the cross entropy loss values into the values. If we add them, it will be equals to 1. That is, softmax function transform cross entropy loss values into the true representation of the probabilities value, so that if we add them, we get the value which is equal to 1. So in this lecture, we also learned that the softmax function for two classes is equal to the sigmoid function. So I hope you understood this lecture. Thanks for listening, and I will see you in the next lecture.